talking about special right triangles. Okay? We're going to talk about a 45-45-90 and a 30-60-90 right triangle. Okay?
I got that.
Okay. So the first one we're going to look at is a 45-45-90 right triangle. Okay. This specific 45-45-90, we were given that the legs are both 1, and then the hypotenuse is the square root of 2. So, using this, we can come up with sine, cosine, and tangent of 45-degree angles. Right? So, it does not matter which of these angles I pick to label my triangle opposite, adjacent, and hypotenuse, because they're the same. So, I'll use this 45-degree angle and say, well, this is the opposite side, this is the adjacent side, and this is the hypotenuse. So, sine of 45, we know sine is the opposite side over the hypotenuse. So that would be 1 over the square root of 2. But we need to rationalize if we have a square root in the denominator. So if I multiply top and bottom by the square root of 2, we get the square root of 2 over 2. It's actually going to be the same thing for cosine. Right? The adjacent side is also 1. The hypotenuse is square root of 2. So rationalizing, write that again, we get square root of 2 over 2. And then tangent. Tangent is opposite over adjacent. So the tangent of 45 is just 1. Right, now, one thing that I'm not actually going to focus on too much in this section, but still want to show you, is that no matter what the size of the sides are for a 45-45-90 triangle, these relationships between the sides still hold. So we can actually say that the side, or the legs, we can call them both x, and then the hypotenuse will just be that length times the square root of 2. Okay. For example, if we have a 45-45-90 triangle where we know that one of the legs is 7. Okay, well, we automatically then know that the other leg is also 7. And then the hypotenuse is just 7 times the square root of 2. Okay, that relationship will hold for every 45-45-90 right triangle. Okay? What we're going to focus on a little bit more, though, is the sine, cosine, and tangent using trig with those angles. Okay. Questions on 45-45-90? All right, then let's take a look at 30-60-90. This is our other special right triangle. So first, let's find our trig functions for a 30-degree angle. So sine, cosine, tangent of 30 degrees. So with respect to the 30-degree angle, we can label the triangle. So the 1 would be the opposite side, the square root of 3 would be the adjacent side, the 2 would be the hypotenuse. So the sine, opposite over hypotenuse, sine of 30 degrees would be 1/2. Cosine, adjacent over hypotenuse, square root of 3 over 2. And then tangent, opposite over adjacent. So 1 over the square root of 3. Again, you need to rationalize. So multiplying top and bottom by the square root of 3. We would get the square root of 3 over 3. And again, these relationships hold, no matter how large the triangle is. If it's a 30, 60, 90, even if this side is 478, the sine of this angle, the relationship between the opposite side and the hypotenuse is still going to be 1/2. Cosine is still going to be the square root of 3 over 2. Tangent is still going to be the square root of 3 over 3. Alright, so let's do the same thing with 60. Oops. I guess there wasn't a slide for 60. So let's do the same thing for 60 then.
Same way I kind of wondering, so it's always going to be those values?
For a 30-degree angle, yes.
Oh. Yeah, that's what, for like a 30, 60, 90, those will always be the sine, cosine, tangent values.
Yes. Because for a 30, 60, 90, this relationship will always hold. So, I mean, if we can call this side x, this side 2x, and this x times the square root of 3. So if, let's say that this bottom side is 7, right, then that would make the hypotenuse 14, and this side 7 times the square root of 3. So in this triangle, if I take the sine of 30 degrees, well, that's going to be the opposite of the hypotenuse, 7 over 14, which is just 1/2. So that relationship always holds in a 30, 60, 90 right triangle. Right. So let's go ahead and find the sine, cosine, and tangent of 60 degrees. And so we can label the triangle with respect to this 60-degree angle now. So now this is the opposite side. This is the adjacent side. This is the hypotenuse. So the sine of 60, opposite over hypotenuse, means square root of 3 over 2. The cosine, adjacent over hypotenuse, will be 1 over 2. The tangent, opposite over adjacent, square root of 3 over 1, or just square root of 3. So these three collections, right, the sine, cosine, and tangent of 30, 45, and 60, are going to be important as we build the unit circle over the next couple of sections here. Right? And again, we're not going to focus too much on this idea, but we need to know that this exists, right? No matter the size of a 30, 60, 90, the relationship between these three sides holds. Right? The side opposite 30 is exactly half of the hypotenuse, and we can just take that side and multiply by the square root of 3 to get the side opposite 60. Right? Questions on our special right triangles? So this slide then here is just kind of a summary of everything we just did. Okay, and then they also include the secant, cosecant, and cotangent of all of those angles. Okay, but those are easily found just by taking the reciprocals of our sine, cosine, and tangents. Right? So again, we'll be using these angles a lot as we build our unit circle, and we will eventually need to have all of this information memorized. Okay, I guess it's not super important that it's memorized right off the top of your head, as long as you understand where it comes from. Right, you can always build the special right triangles and figure out all of this information. It'll just be a little quicker if you have it memorized. Okay. Questions? All right, so our co-function identities, and these will make a little bit more sense as we get into the graphs of these functions, but probably be a good idea to jot these down now. Sine is just equal to the cosine of pi over 2 minus the angle that we're talking about, or if we want to talk about degrees, pi over 2 is the same as 90 degrees. And pi over 2 radians is 90 degrees. So in each of these identities, we could just plug in 90 degrees instead of pi over 2. We want to talk about degrees.
So, why are we using degrees and radians? Why wouldn't you get what I'm saying?
Sometimes,
Like in that formula, because it says that the angle is supposed to be in radians.
so when we use like our arc length formula or the area of a sector formula that we talked about, the angle had to be in radians. But sometimes I guess it's kind of like thinking about the English system of measurement versus the metric system. The metric system probably makes more sense, but we're conditioned to think in terms of the English system. So, like, even if we're given something in metric, we think, oh, how many? We said 17 kilometers. Well, how many miles is that? It makes more sense to us to think in terms of miles. So, even though radians might make more sense, it's easier for us to think in terms of degrees, just because that's what we've learned for our whole lives. That's my explanation of it. So a simple example of something like this, we could say that sine of 33 degrees is equal to the cosine of 90 minus 33 degrees, which would be the same as cosine of 57. So the sine of 33 degrees is the exact same value as the cosine of 57 degrees, right? And the reason that that's true, if we've got a right triangle where we've got a 33 degree angle and a 57 degree angle, and these aren't actually going to be the values, but say our sides are 5, 6, and 7. Well, the sine of my 33 degree angle here, actually, let me use variables so that those numbers aren't actually wrong. How about A, B, and C? So the sine of 33 would be opposite over hypotenuse. That's going to be A over C. Well, this angle, the 57 degrees, the cosine of that will be adjacent over hypotenuse. It'll be the exact same thing. Okay? That's where all of these co-function identities come from. Okay? It's just thinking in terms of a right triangle. And if I know that this is a 90 degree angle, these two angles would have to add to 90. So if we're taking an angle and its complement, the sine and the cosine will be equal to each other. Same thing with the rest of these relationships, right? The tangent and the cotangent of its complement will be the same. The secant and the cosecant of its complement will be the same. Right? Questions on that idea? All right. So, here's a couple other simple examples. If we're given that the cotangent of 68 degrees is about 0.4040, we want to use that to find the tangent of 22 degrees. Okay, well, one of our identities on the last page was the cotangent of theta is equal to tangent of theta, or 90 minus theta. So if I take plug 68 in for theta, minus 68, we can see that 90 minus 68 is 22. So the cotangent of 68 is equal to the tangent of 22. So if the cotangent of 68 equals about 0.4040, the tangent of 22 also equals about 0.4040.
I'm gonna keep doing.
Right? So B then doesn't give us any actual values. It just says find the exact value of cosine of 72 over sine of 18. Well, using our identities, we could say that cosine of 72 is equal to the sine of 90 minus 72. So cosine of 72 equals sine of 18. If I know those two things are equal to each other, what is their quotient equal? 1. Right? If I have two things that are equal to each other and I'm dividing them, that's just going to be 1. And I don't need to know what the actual values of these things are. I just need to see that they're equal to each other. So if I'm dividing something by itself, that's just going to equal 1. You okay with something like that? Going great on time. All right, so the book then actually jumps right into applications. We're going to throw in an intermediate step in here and solve right triangles before we look at story problems. So if we've got something like 37 degrees. Let's start. Right. A right triangle like this. And our goal is to solve for x. Right? If you took pre-calc last year, you solved problems like this, but if not, it's been since geometry, since you've seen something like this. Right? So, what we want to do is use trigonometry. We need to set up a trig function. To figure out what trig function we need to label the triangle. So with respect to this 37-degree angle, I want to label the two sides that are in question. So the 15 is the opposite side. The x is the hypotenuse. Okay, the adjacent side isn't part of this problem at all. So if I'm dealing with the opposite side and the hypotenuse, which trig function is that? I heard a few whispers of sine. So the way that we're going to set this up is the sine of the angle, so sine of 37 degrees, equals opposite over hypotenuse. Now, I just need to solve for x. So, to solve for x, we want to get the x out of the denominator. So multiply both sides by x. And then, divide both sides by the sine of 37 degrees to get x by itself. So, these cancel then, we end up with x equals 15 over the sine of 37. Okay, we'll need a calculator for this. Right? Sine of 37 isn't something that we would know off the top of our heads. So we'll need to put in 15 divided by the sine of 37 into the calculator. Now, this is a good time to talk about the mode of your calculator. You need to make sure that if we're doing a problem with degrees, that your calculator is in degree mode. Okay, so you press the mode button up at the top. The third option down is radians or degrees. The default mode is radians. Okay, so you need to make sure that you check to see that your calculator is in the correct mode before plugging something like this in. So you end up with 24 points. Let's say we'll round things to 3 decimal places. Okay, round to 3 decimal places. So, oops, I put a degree sign, didn't I? It's not degrees. 24.925 would be the length of the hypotenuse. Okay. Questions on something like that? How about something like this? We don't do sig figs.
I know, but like how to do it.
I think so. Alright, so give this one a try here. Okay, solve for missing side.
Or you could do 90 minus 60. And then do 10. Yeah.
It is true. Yes.
You know I don't think
Did we get 5.412 for x? Right, do we feel comfortable solving for a missing side? Alright, let's try 1 or 2 then where we're solving for a missing angle. Right? For something like this, where we want to solve for a missing angle, we're going to start the same way. Okay, with respect to the angle that we want to solve for, I'm going to label the sides that I'm looking at. this would be the adjacent side. This would be the hypotenuse. So then we want to choose our correct trig function. So adjacent and hypotenuse is going to be cosine. So we're going to say cosine of the angle equals adjacent over hypotenuse. Okay, it's set up the exact same way as if we were solving for a side. But now I need to get the angle by itself. You remember how we undo a trig function? Take the inverse trig function. So we're going to take the inverse cosine of both sides. So inverse cosine and cosine cancel out. And we get that our angle is equal to the inverse cosine of 2 over 13. And what? 81.150. Right, so the inverse cosine is right above the cosine button on the calculator. Right? We did second cosine, and then 2 over 13. We get that missing angle is 81.150. You okay with that process? Alright, you guys try one then. Find this angle given about something like that. Find the missing angle. We're just going to practice the stuff that we talked about on Monday. So, yeah.
That wasn't very hard.
So we're setting this up the same way that we did if we were solving for a side, right? Label the sides with respect to the angle. So this is adjacent, this is hypotenuse. So I'm going to use cosine. So I'm going to say cosine of the angle equals 2 over 13. But then
I've literally done this so many times.
to get the angle by itself,
Probably this is the
I
third
need to
time.
undo cosine.
So I haven't paid attention.
To undo cosine, I take the inverse cosine. So I need to do that on both sides.
It's great.
So those cancel out.
Mr. Fach, this is the third year I've done this.
Yeah, geometry, pre-calculation, CCP trig.
It's amazing. It's so great.
Should have it down then.
I haven't paid attention at all, and I did this without really thinking about it, so I feel pretty good. I feel like it's a muscle memory right now. Do you ever feel like your arms are gonna fall?
No. I feel like my arms are gonna fall off. I feel like I'm gonna fall asleep.
I'll try to get that.
having
It shouldn't take me too long. I can do that next period. I'll try to get that in.
I want 8th period. I love that. I really love that.
I'm so happy today's the last day of school.
Really?
Did we get 23.288 degrees?